And here is the solution to problem of the day posted on 7/1/26. Okay, part A was use the product rule to prove that the covariant derivative of this tensor, the product, is equal to that. Okay, so the first thing we want to do is do the product rule, perform the product rule. Okay, so we have the first times derivative of the second. All the derivatives are covariant derivatives. Then the second times the derivative of the first. Now we want to break out what that is and what this is, okay? So we want to expand the covariant derivative using the rules. Oops, I cut off the S. No, nobody cares. Okay, here we go. So we have one contravariant index, which means we need a plus sign. And remember the rule. When you have a plus sign, the summation index goes low to high, low to high. It's easy in this case because we only have two free indexes, J and K. So the J could go here or there, but you know it can't because this is a summation index. So it's just JK. Okay, now we do the contravariant component. So when we have a contravariant index, the summation index goes high to low, high to low. And that makes this easy. It's just IK. Okay, now let's put that back in, substitute into the original equation. We get this. All right, so I just took these two things and put them in there and there. We get this. Distribute the terms, and we get this. Right? So I multiplied this by this term, this by that term, and I got these four terms. Now, combine like terms. What I mean by that is this looks like that, and this looks like that. And we get this. Now look at this term in blue. What does this look like? A coefficient times a derivative plus a coefficient times a derivative. That looks like the product rule, right? And it is. It is the partial derivative of AI bj with respect to the coordinate xk. Okay? So that was it. That is the proof. Rearrange the products so that they look like they did when I wrote them down by bringing the Christoffel symbols outside. And there's the final answer. Okay? Part B, using the proof from Part A, prove that the covariant derivative of this tensor product where the indexes are the same, so this is a summation index, meaning it's fully contracted, fully contracted. Prove that that's equal to that, okay? So what we're going to do here is, since we know how to do it from the one above, we don't have to go through the product rule anymore. We take the partial derivative of this with respect to the coordinate, and we have two indexes, one contravariant, one covariant. So we have a plus and a minus, right? We put in our summation indexes the way we're supposed to, low to high, high to low. But we also have now this summation index, I, right? So what are we going to do about that? Well, since these are summation indexes, this term in blue here, I can just change I to M and M to I. And it looks like this, right? So this is exactly the same as that. So this cancels that, and we're just left with this. So what does that mean? That means that the covariant derivative of a scalar field reduces to just the partial derivative. This is just a scalar field, right? Because it is a full contraction, which means it's a scalar, a tensor rank 0. And once you have a tensor rank 0, then the covariant derivative is the same as the partial derivative. Okay, I'll see you later.